So our first speaker today is Youngkee Yin from NICS. And Youngkee's been working with PI Frank Skidmore at the University of Alabama, Birmingham on fMRI image registration. And what this involves is you have brain images and you want to be able to compare these across collections of data, specifically looking for problems versus kind of more control subjects. And what Youngkee's going to tell us about is some of the optimization work that's been done to make kind of the registration process, which is a very important component of this, more feasible for the PI. So I think with that, we'll let Youngkee take it away and tell us about his work.
Okay, thank you, Nancy, for the detailed introduction. Hello, everyone. My name is Junqi, and today I will share some experience working on one of my ECSS project on brain image registration with AFNI's 3D QWarp. So the outline of my talk, first I will briefly introduce what is AFNI and the image registration. Then I will talk about the image registration code 3D QWarp within AFNI and show some profiling and the benchmark results, based on which then I will show our implementation for the optimization for OpenMP structure within the code and our improvement of the warped image fidelity. At last, I will show some results on both scaling and PI's research. So AFNI, which is analysis of functional neural images, it is a community software package. It's maintained by NIH, and the first paper introduced this code was published in '96, and it currently have over 5,000 citations so far. And I print the citation map. As you can see in the citation map, it's widely used in US, Europe, and East Asia. So it's a very popular community code for neuroimaging analysis. So briefly, what is image registration and why do we need it? Suppose in one of the typical neuroimaging analysis is we want to analyze for different subjects across different images, and the first step, which is important step for the pre-processing, is to normalize this image. When I say normalize, it's also register, or somebody also called it warped image. And basically, it is register your input image to a given template. Let's say, because different subject could have different, let's say, brain size, or when a subject taking the MRI scan, he could tilt his head, etc. For example, if you look at this input image, it's obviously a slightly tilt. And we want to, if we want to analyze different subjects, even for the same subject during different time, first step is to register to a template, which is shown in the middle. And the output of this image registration step would be, look at the right column. As you see, it's nicely registered with respect to the template. So the basic flow chart of 3D QWarp is you load the image, you divide the image into smaller patches, you optimize the patches with some kind of optimizer, and basically in the AFNI's 3D QWarp code, it's a line search. You update patches one by one. If all the patches is updated, then you check whether it is your desired patch size. If it is, then you generate the warped image and your warp, which can be applied to other signal of the same image. So if we look at the function core chart of 3D QWarp, basically 3D QWarp is about 10,000 lines within the AFNI code. and Afni is a huge package. And for the optimization function is basically it's they call a warpmatic, with basically image warping, 3D image warping optimization for the warp. Then it calls the main function, as I show, which updates the individual patch, which is IW3D improved warp. It will iteratively call this function and gradually reduce the patch size. Within the same patch, it will call an optimizer. In this case, they use Power and EWall. It's an iterative optimizer, which is another iteration procedure. So there are two iterations, as you see from this function call chart. And in this call chart, the red color indicates the function is optimized, is parallelized with OpenMP. So you see the problem, right? So basically the parallelization level is at the bottom of two iterative procedures. Now let's see some benchmark and profiling results for the 3D QWarp. In this chart, on the x-axis, I show the patch size. Basically, it gradually reduced, and the y-axis is the wall time. So as you can see, when the patch size is sufficiently large, the runtime is more or less the same. And when you reach the smaller patch size, the runtime basically explodes. And for PI's research, PI want to do like basically voxel-wise comparison. So the desired patch size for PI's research is 3 mm by 3 mm by 3 mm, which will take a few days to a week to complete. That's why they reach out to ask for ECSS support. So if we do some basically benchmark and profiling, and for a patch size about 25 by 25 by 25 millimeters, it looks sort of okay on the Xeon side, which is about 70% efficiency. If we compile the code and run it natively on Xeon Phi, you see it's already the code actually performance decrease after about 40 threads. And the problem becomes even worse when the patch size reduced. So previously I showed for 25 by 25.
Jay, could you mute everyone, please?
Okay, thank you. So for the previously I showed for the patch size 25 by 25, it's about 70% efficiency. When we reduce to the patch size 5 by 5, as you see by this yellow curve, it's actually less than 30% efficiency on the Xeon side. Here, let me list the profiling results. The hotspot function for this procedure, you will obviously see, as I show in the function call chart, the hwarp, the hottest function is hwarp apply, which is called by the cost function. Basically, it's the cost function invoked by the global optimization procedure. It's about 40%, and another about 30% was basically OpenMP overhead. It's OpenMP barrier and the launching threads, and another about 25% was spent on energy calculation, which is also called by the cost function. So by identifying the hotspots and of this code, and we see the flowchart and the call function, immediately we have some idea how to optimize this code. So some consideration is for large patches size, basically threads have enough work to do within the patch. So it is okay, your parallel level is on the bottom side. While for the smaller patch, there are just too many patches, and each only require little computation. So one way to improve the parallelism is to add another parallelization layer on the patch level, basically across the patch, not just within the patch. And we use a nested OpenMP structure, and because this workload distribution for small and large patch sizes, we need to dynamically adjust the thread size on 2 layers according to the current patch size. And for each group of threads within the same patch, they will have the same view of the image, and we synchronize them after one sweep of all the patches. And for the same patch, basically we do 4 sweeps to ensure the information is flow across all the patches. So obviously the one of the most tedious step is to treat global variable. I think that's like a typical problem for many community code, legacy code, because it's not up to the software engineering standard. There are a lot of tons of global variables. They even use goto statements, and to make first we need to make sure all the threads are working on their own memory space of the patch. So we need to identify all the global variables, make sure each thread and declare them thread private, make sure each thread has a copy, has a view of their own patch. And this is most tedious step in this process. And once that's obviously we need to use some software like Intel Inspector to make sure there's no data race across different threads, across different patch. And then for the patch size level across different patches, as you see, at least the routine several lines from the warp optimization function calls, it basically look different level correspond to different patch size. So we need to divide the work depending on the patch size. We define a patch thread, which will be, it's a sort of empirical, it's a power law. Basically for the first 2 levels, it will be just 1 thread because it's just too little patch to distribute. The overhead trumps the distribution of patches. And for the another constraint is that obviously the patch thread should be smaller than the total number of threads to ensure there's no oversubscription. And then within this level, within the same level, which is within the same patch size, we have to call basically 4 for loops. And each use the number of threads each patch thread specified in the previous steps. So this is the parallelism we add across the patch. Within the patch, we just need to adjust the number of threads to be total number of threads divided by the threads number on the patch level. So another consideration is to improve the warped image fidelity. By default, I guess it's from the consideration of speed. The original code just did 1 sweep update of all patches, and then reduce the patch size, go to the next level. And to improve the image fidelity, we add a convergence criteria. Basically, the cost function for this optimization procedure has 2 parts. One is correlation, the other is penalty. So correlation is between your warped image and your template. So that's the real quantity we want to optimize. And there's a penalty term, which basically, in this case, defined as elastic energy. It's to make sure that you don't get unphysical results, like move the voxels like far apart. for example. So what we want is to maximum correlation within certain penalty. Basically, we just add like a loop check between you goes to the next level. Basically, we want to make sure the penalty is smaller than certain value. We will continue to do the update until certain level of convergence is reached. So just by simply adding this, we see about 20% improvement in terms of Pearson correlation coefficient. I'll show what that means in the later slide on PI's results. So here, let me show you some scaling results just by optimizing the OpenMP structure of this code. In this plot, the orange plot are basically for the optimized code, and the purple ones are for the original code. As you can see, I show two different patch size. One is 9 by 9 by 9, while the other is 5 by 5 by 5. So for both sides, the original code already performance actually decreased past over 8 threads, and we see a nice scaling for the optimized code. This is using this is on to Xeon E5 16 cores. And even when we turn on the hyperthreading, we can still see some performance boost. It's more obviously for a smaller patch like 5 by 5 by 5. If we go to the 3 by 3 by 3, which is take a long time to run, I didn't show in this plot, it will be even better. So from this plot, you can see with the optimized procedure, we get about 5 times speed up comparing to the original code. Now let's compile this code natively and run it on Xeon Phi. As I showed before, for this size, like 9 by 9 by 9, it's not that small. Original code already performance actually decrease when you increase the number of threads. By simply optimize the OpenMP structure, and we get about 2 times speed up on Xeon. Obviously, there's still a lot of work to do because it's still about 2 times slower comparing to the original code on the Xeon. So what does that mean on PI's research? How does the improvement in registration help with PI's research? So we know that the 3D QORB originally is basically bottleneck for PI's analysis pipeline because it takes about over a week. And for the original procedure, there is a predefined quality control step in PI's analysis pipeline. Basically, to check whether this image is sufficiently registered. If not, it can be used for downstream analysis. So for the original procedure, it takes a long time, and only 66% of sample images pass the QC. And with the optimized procedure, over 98% of sample passed. So basically, this difference you can visually see from this image. In this image on this slide, I show in the leftmost column is the raw image without register. So it has 101 subjects with Parkinson's disease. You see, when we basically do a mean across this average image without registration, you see the signal is blurred across the whole image. You basically cannot use that image for downstream analysis. And in the left second column is the traditional registration, which use affine transformation. It's a linear transformation procedure. It's slightly better, but still looks blurry. So you can see the visual difference. And for the third column from the left, it is the mean warped image from our optimized warping procedure. And the rightmost, the fourth column is the template. As you can see, our optimized warping procedure generate 100 image and the mean average. We still see a good signals, and it's comparable to the original template. Remember, template is use image from healthy subjects, and our warping actually is for 100 Parkinson subject with Parkinson disease. So what does this high fidelity warping means for the downstream analysis? You can see with this improved warping procedure, PI is being able to identify which portion of the brain can be used as an indicator for the early Alzheimer, early Parkinson disease a symptom. As you see from these two plots, the colored voxel basically indicates that it is basically a two-sample comparison between healthy subject and patients with Parkinson's disease, and look at which voxel can be used as an indicate clear difference between the control subject and the subject with the Parkinson's disease. And with this improved warping, we can clearly see the temporal tip region and the brainstem region can be used even for the early progression of Parkinson's disease. So the future work of this code, obviously, to make it more efficiently Xeon Phi, we need to considering the vectorization of hotspot routines. And another consideration would be the distributed computing, because they're currently still a single node. That's all I have for today. Thank you for your attention.
Junki, thank you very much. That was a fabulous talk. Really, really interesting. I think you touched on some issues that many ECSSers probably encounter in their work, especially working with large established community codes, and the size and the complexity and the software engineering approaches used or not used in some of those codes. I wonder if you could say a little bit about what it was like working with the research team on something this large. Did the changes get incorporated back into this community code base that others will then go on to use, and that sort of thing?
Okay. So right now, this optimized procedure is currently just for this team from UAB, and it is being used for their analysis, and they generate nice results to report on their funding agencies using this procedure. And yes, that's the plan. The plan is to, we will eventually incorporate these changes to the original community code. Actually, we are in contact with the developer of AFNI at NIH, and it will be incorporated.
Yeah, very good. Let me open it up to others for questions before I ask one more. Does anyone else on the call have questions?
This work was performed on Beacon, I think?
Yes, mostly on Beacon.
So do you have any plans to actually use XSEDE resources?
I think for the next step analysis, they will use XSEDE resource for production runs.
Because the startup gets in May, so I guess they'll have to decide what they want to do.
Yeah, that's right.
Thank you.
Thanks, Sergio. Any other questions for Jinky?
Yes, Nancy, this is Bob. I have a couple of questions. So, First of all, what did you use to, how did you profile the code? What tool did you use?
We use Intel V2.
Intel V10, okay. And also, earlier in the talk, you were talking about the two types of parallelization that you could do. So the original code, it used threading within a patch. Hold on a sec. It used threading within the patch, and then you developed a new scheme where the threading was over patches. Did you find that there was a kind of an intermediate regime where, I don't know, maybe 12 cubed or 15 cubed, where neither type of parallelization was quite optimal?
There is a trade-off between two level optimization. That's why we use a dynamic scheme to adjust the number of threads on each level. For small patch, obviously, the parallelization is more efficient if it's cross-patch. For large patch, the thread will be more efficient if it's working within the patch.
Okay. Oh, okay. So I didn't quite catch that when you when you covered this slide. So you do have the two levels of parallelization. You're always having a trade-off between the number of threads used
across
to distribute across patches and within. Okay.
Yeah.
Okay, thank you.
Sure.
Oh, and finally, one last question, if you don't mind. You mentioned in one of your slides hyperthreading. And do you find for this code that hyperthreading was more efficient?
For our optimized procedure, we suggest the user to use hyperthreading.
Okay. Oh, interesting. Because I know that most scientific codes don't benefit from hyperthreading, but it's nice to see that it worked here. Of course, for XSEDE resources, I believe that most of them, with the exception of Darter, have hyperthreading turned off. But this could be a good case for arguing that a certain subset of nodes on our resources should have the hyperthreading turned on.
Right. And on Darter, you can also use hyperthreading. Just it's not the default setting.
Okay. Yeah, I just know that with the hyperthreading, to switch between using and not using hyperthreading, that the node needs to be rebooted, and it's a change as a BIOS.
Right.
Okay. All right. Thank you. That's everything.
Yep. Thank you.
Great. Thanks very much, Bob, and thanks, Jinki, for a terrific presentation. Let's go ahead and move on here. I'd like to give Lee enough time for his talk. Lee, can we test your audio from Ritu's machine?
Okay. Can you hear me?
We can. That's terrific. Can you also try clicking on the button at the bottom of the screen that says present? It's got a little picture of a display, and we'll see if we can get your slides up.
They're about to lose program. It's a PowerPoint file. It's a PDF file. Okay, I can send you. Okay. But I don't know whether it's come back or not. Okay, let's try the add attachment.
Thanks, Ritu. And so Lee's going to be talking about work with PI Dr. Ramkrishna from Purdue, and the work is around an open source molecular dynamics package of Dr. Ramkrishna's that performs quite well. They've seen a 9 times speed up over LAMPs in particular scenarios. It looked like the display was starting to work there. You guys seeing anything from your side, Lee?
We are trying to figure out how to present the PDF file. Desktop. Okay, yeah. That should work. We just present, and then you can switch.
Can you see my desktop?
Just about. It's coming on through. Yeah, very good. Okay.
Great.
If everyone else could also mute, that would be great.
Display model. Yeah. Yes. Yes. Okay. Great. Thank you. Thank you so much for your help. Yeah. Hello, everyone. I'm going to talk about the ECSS project I worked in the last summer, boosting molecular dynamics with advanced hardware and algorithms. Here is the outline of my talk. First, I will go to talk about the background, such as molecular dynamics and the status of the code when I started the project. Then I'm going to go through the improvement we made and the lessons we learned from this project, and then to summarize. Since some of you may be not familiar to molecular dynamics, I'm going to briefly talk about the molecular dynamics simulation and the common workflow. Molecular dynamics is a technique for computing the equilibrium and transport properties of many body systems, such as a box of molecules. As shown in the cartoon on the right side, every particle is interacting with others. Oh, okay, here is just a picture in the PDF file. Given the initial coordinates and the velocities, the system can evolve according to Newton's second law of the equation of motion. There are several different integration algorithms available. On the left side, it shows the Verlet scheme. At the beginning, the initial position and the velocities are provided, and we can calculate the forces and accelerations. Then we can get the coordinates for the next time step based on the current coordinate and the velocity and the acceleration. After that, we need to update the forces based on the new coordinates. And then we can calculate the new velocity for the time plus t plus dt based on the current velocity and the old and the new accelerations. And then the time move forward to t plus dt. Now, one empty steps is finished. Such procedure is repeated as long as one needs. Generally, one empty step takes about tens of milliseconds to several milliseconds. Most simulations need millions of empty steps. To start systems, simulations based on empirical force fields are widely used. Force field is a set of equations to describe atom-atom interactions and associated empirical parameters. The Hamiltonian shown here is widely used by many programs. It generally includes bond stretching, angle bending, dihedral potential, improper dihedral, and charge-charge interactions, and van der Waals potential. Bounded interactions include the first four terms: bond, angle, dihedral, and improper dihedral. They are short-range interactions. Only local atoms are involved. The non-bounded interactions, Coulomb and van der Waals interactions, are the most expensive part in calculations. For van der Waals interactions, the value quickly decay to zero when the distance increases. We can choose a cutoff distance and only calculate the pair interactions within such chosen distance. We were going to talk about the Coulomb energies with more details later. Forces and accelerations can be calculated with these two equations. Stampede is the first large cluster equipped with Intel Xeon Phi core processors. It is also named as MIC, short for Many Integrated Cores. A typical node on Stampede contains a host component and a MIC component. Host has two sockets, Intel E5-2680. There are 16 cores in total. They are running on 2.7 gigahertz, 32 gigabyte memory available. All computer nodes has at least one Intel Xeon Phi as a PCI Express card. There are more than 400 nodes have two mic installed. Each mic has 61 cores supporting 244 hardware threads running on 1.1 gigahertz. There are 8 gigabytes memory. In terms of double precision floating point instructions, the host has about 0.35 tera floating point operations per second. One mic has a little over 1 teraflops. Mic potentially is able to boost applications noticeably after the code is carefully tuned. This table shows a non-complete list of the modules supporting mic on Stampede. They include libraries, profiling tools, etc. At the very beginning, AMD and LAMPS are the packages for molecular dynamics simulations. The code for mic was optimized by the staff at Intel. From our tests, generally using mic could provide around 1 time speed up compared to only using the host. Although there are several open source packages available for general purpose AMD simulations, such as AMD GrowMax and LAMPS. However, researchers still need to develop their own AMD engines under special circumstances. Dr. Thoreau Swami at Purdue University developed a package of molecular dynamics for the crystallization of organic molecules. When I was assigned to the project, they already had a code supporting mic with synchronized offload for neighbor lists and non-bounded interactions. The calculations of bounded terms were parallelized with OpenMP for each component. With profiling, I noticed that the code spent a lot of time on I/O. I also found some issues on the algorithms they used. They are using the 1 femtosecond integration timestamp since they did not implement the shake algorithm. They were not using advanced algorithms such as particle mesh EWall for long-range electrostatic interactions. Instead, they use an algorithm named as damped shift forces. This method needs large distance cutoff and provides inferior accuracy. In the following slides, I'm going to go through the improvements we made one by one. We majorly focused on the optimization on one node, especially for one socket on Stampede. Later, we developed the hybrid code using MPI and OpenMP to utilize more than one node. Let's start from the buffered I/O. With Intel Photon compiler, buffered I/O is used by default. It is convenient to debug code and is robust for unexpected hardware or software failure. However, the performance could be much lower than using buffered I/O. To enable buffered I/O for Intel Fortran compiler, there are two different ways. Either you can provide a flag, assume buffered I/O to the compiler when you build your executable file. Alternatively, you can choose using the unbuffered or buffered I/O at runtime to set up the environment variable. It is very convenient to switch between two modes. And we got about 40% performance increase with buffered I/O. Bounded energies includes 4 components: bound angle, dihedral, and improper dihedral energies, as well as several correction terms. In the original code, each component was parallelized with OpenMP, but they did not scale well. And we tried task parallelism in OpenMP. Separate task is created to tackle individual bounded terms, and all tasks run simultaneously. The performance improved by around 10%. In molecular dynamics simulations, 1 femtosecond time step is needed for flexible bonds with hydrogen atoms involved due to the low mass of hydrogen atoms. The simulation using larger time steps are not stable, and the total energy does not conserve well. Additionally, shake algorithm can be employed to fix the bond, and for the hydrogen atoms involved, then we are able to use the 2 femtosecond time step to boost simulations. And we got performance improved by 98%. The non-bounded interactions, especially the electrostatic interactions, is the most expensive part in MD simulations. An algorithm named as damped shifted forces was used because the algorithm is very straightforward to implement. However, this method needs large cutoff and provides inferior accuracy. In widely used MD packages, an algorithm named as particle mesh EWall or its variant is used. I'm going to briefly introduce this algorithm. Consider a box of charged particles with periodical boundary conditions shown in the left side. The volume is L to 3. How can we calculate the overall Coulomb potential? For short-range interactions, like van der Waals energies, we generally can choose a cutoff distance to truncate potential. The tail correction can be calculated with an integral shown on the right side. This method works well for van der Waals energies. However, it is not suitable for Coulomb potential, since it decays too slow as 1 over R. More advanced technique is needed for Coulomb energies. Currently, prevalent algorithms like PME were developed based on the EWall summation method proposed by EWall 95 years ago. Here is the cartoon to demonstrate the basic idea. Each point charge can be represented as the original point charge plus 2 Gaussian charges with opposite sign. The electric field generated by the left system is equivalent to the sum of 2 systems shown in the right. The other one is the short-range terms. the sum quickly converges in real space. The lower one is the long-range terms. The sum can quickly converge in Fourier space. Then the Coulomb energies can be calculated with this equation. The first term is the Fourier space summation. The second term is self-energy correction. The last term is the calculation done in real space. Standard EWall implementation scales like n to 2. The most expensive part is the Fourier transformation. Using fast Fourier transformation does help. There are 3 popular algorithms like FFT with FFT implemented, like P3M, PME, and SPME. They scale like n times log n. The implementation of PME code is not trivial at all. So I started with a serial version of the PME code from packages named as MDX, developed by Klaus Schutten's group. As the UIUC is using the same algorithm that's used in AMD. With OpenMP, I have parallelized 4 functions, and the PME calculations scale reasonably well with core numbers up to 8 cores. With PME, the performance is improved by 92%. With synchronized mic offload, the host essentially stays idle when the mic is working on offload tasks. It is very straightforward to convert the code into asynchronous mode. First, define the variable and initial it as the signal, then use signal in the directive of mic offload. Last, wait for the signal we define. Compare with the synchronized offload, we get about 54% for performance. Building neighbor list is also time consuming, so we tried improving the criteria to rebuild neighbor lists. Rebuilding neighbor lists when any item has moved a distance larger than Rm minus R cut, the skin region. Since last, the neighbor lists building. Generally, one algorithm is 1 angstrom is large enough for the skin region. With the new criterion, the performance is improved 15%. I also would like to share a lesson we learned from running mic offload and decode in this project. Here is the issue we found. The pneumo control for CPU binding to a socket imposes large performance penalty, more than 30% compared with the case without pneumo control, when the job is using all cores of one socket. We found the issue is gone if we leave at least one core on the socket idle. Then that means the available CPU resource is important for the thread dedicated for the asynchronous mic offload. Here is the table to summarize the improvements we made for this code. Overall, we got about 9 times speed up by using buffer I/O and introducing several advanced algorithms. Other than this, we also helped the PI develop NPI OpenMP hybrid code to utilize more than one node. I would like to thank the PI, the graduate students of this group, Connor Park, and Dr. Wang at PSC, and Dr. Liu at TAC. Thank you very much for your attention. Any questions?
Lee, thank you very much for an excellent talk. Do we have any questions from the audience before I jump in with a couple of my own?
Yeah, Nancy, this is Bob again. I got one question. So again, I thought that was a great talk. I can't believe how much work you did on this project. But I do have a question. Maybe this is more for the PI. What was their motivation for developing their own MD code, given that there are other codes out there?
I think they would like to try some novel algorithms or try some new stuff that is not available in the traditionally available packages.
Okay, and the other thing, and this may be more of a comment than a question, all of the work that you did in code was great, but the fact that they didn't use the shake algorithm in there, or they didn't use the PME. So a lot of these things that I think were, just very standard in mature MD codes. So just a little surprised that they didn't implement those from the beginning.
Mm-hmm.
All right, thank you.
Thank you.
Yeah, thanks, Bob. It sounded to me, Lee, like you were really involved from a very intellectual level from the domain side as well as the optimization side. So I just kind of wanted to comment on that and how that went. And I was also surprised. I liked very much the way you broke out the different components of this speed up, and I was surprised that the buffering provided such an improvement, and it made me think about other codes that could also benefit from something that simple.
Yes, yeah, for the buffered I/O, it's pretty common. Sometimes it can provide many times, like more than 20 times speed up. Yeah, for some special cases. Yeah, sometimes it really depends on how heavy the I/O for the program. Sometimes maybe just several percent.
Yeah, it is interesting. It makes me think whether we want to do something kind of I/O focused for the user. So some of the different strategies that we've seen been effective in ECSS, from the simple to the more complex, is kind of a, I'm not sure how much sense that makes from a general overview perspective, but it might be an interesting topic.
Mm-hmm. Yeah. Yeah, generally we can just use very simple profiling to check whether there are I/O issues.
Yeah, kind of speaking of that segues a little bit into the topic for next month's symposium. So Tom Furlani from the University of Buffalo and the XSEDE mod group, they are going to be doing a demo for us. Let's see, it's single job use of XD mod. So instead of looking at statistics on a machine as a whole, you can now look at individual statistics for a particular job. And I think that's going to be interesting for a lot of us on the ECSS project for, what we can learn, what users can learn, how effective this can be used in some of our projects. So stay tuned for that. Next month. Do we have any other questions for Lee? Okay, great. Thank you very much for joining this month's call.